Hello guys, in this video I am going to explain to you the concept of limit of a function, which is a super important concept and is the base of all the calculus. But despite being super important, it is quite easy. In order to explain the concept limit of a function, let me take a function here. Let me take a function f(x) equals x square minus 4 divided by x minus 2. Now you can say that this function is same as gx equals x plus 2. The reason being that x square minus 4 can be written as 2 square. X square minus 2 square is x minus 2 into x plus 2. X minus 2 cancels out from numerator and denominator, and we are getting f(x) to be same as x plus 2. But then I will say, wait a second, just look at g at 2. That means we will replace x by 2. So g of 2 will be equal to, just replace x by 2, it will be 2 plus 2, that's equal to 4. But if we look at f at 2, that will be equal to, this will be just replacing x by 2, this will be 2 square minus 4 upon 2 minus 2, that will be equal to, this 2 square is 4 minus 4 upon 2 minus 2 is 0, that is equal to 0 by 0. So g at 2 equals 4, but when we look at f at 2, it's equal to 0 by 0, an indeterminate form. So f(x) and gx are different functions, or in other words, we can say that f(x) and gx are two same functions other than x equals 2, because at x equals 2, g of 2 equals 4 and f of 2 is an indeterminate form. So f(x) and gx are same for all x's, but not for x equals 2. If we look at the graph of this function, let me first rub out this. If we look at the graph of the function f(x) equals x square minus 4 upon x minus 2, its graph will be just like this thing. This is the x-axis, this is the y-axis. We see that for x not equal to 2, f(x) and gx are the same functions, but for x equals to, f(x) is undefined and gx equals 4. So the graph of the function is like this. It is same as x plus 2, which is the line here. You see that this is the line which is at a distance of 2 from origin towards the y-axis, and the straight line like this, because at 0 it will become 2. You see, at 0 it becomes 2, so it is like this. But at 2 we have a hole here, because at 2 it's not defined, so hole represents here that the function f(x) is not defined at x equals 2. Next, what we will be doing is, we will be considering the pointers which are to the left of 2 and to the right of 2, to the left of 2 and to the right of 2, but close to 2. And at those pointers, we will be looking at the function values. That means to the left of 2, we will be taking pointers, for example 1.9, and looking at f of 1.9, 1.99, and looking at f of 1.99. And similarly, to the right of 2, we will be taking pointers 2.1 and looking at f of 2.1. 2.11, looking at f of 2.11, and we'll be recording all these things in a table. So here's a table. This side represents when we take points from the left, this column represents the axis we will be taking, and this side represents the function values. Similarly, this is when we take points from the right. Let me take the first point as 1.9. If we look at f of 1.9, it will be just replacing x by 1.9 in this function. So it will be 1.9 square minus 4 upon 1.9 minus 2, which can be easily calculated on a calculator, and this will come out to be 3.9. So when we take x at 1.9, the function value will be equal to 3.9. Similarly, next point I will take to the left of 2, but much more closer to 2, I will take 1.99. When we look at f of 1.99, it will be simply 1.99 square, because the definition of function minus 4 divided by 1.99 minus 2, that will be equal to 3.99. So here I'll be getting the point 3.99. Next point we'll be taking is 1.999. Similarly, the function value will be 3.999. Next point is 1.9999, and the function value we'll be getting is 3.4 times 9. Last point we'll be taking as 1.5 times 9, and the function value we'll be getting as 3.5 times. Next, we'll be taking points which are to the right of 2 but close to 2. As a first point, we'll be taking 2.1. When we look at f of 2.1, it will be just 2.1 whole square minus 4 divided by 2.1 minus 2. When you calculate it, it will come out to be 4.1. So the function value at this point is 4.1. Next point we'll take is 2.01, and the function value will come out to be 4.01. Next point 2.001, the function value will come out to be 4.001. Next point we'll be taking is 2.0001, and the function value will come out to be 4.3 times 0, 1. The last point, which is to the right of 2 and much closer to 2, will be 4 times 1, and here 4 times 0, and here it will be getting 4.4 times 0 into 1. So let me first start about these calculations. From the first two columns of this table, what we observed is that as x goes closer to 2 from the left, f(x) comes closer to 4, and that's also clear from the graph. You see, as x goes closer to 2 from the left, f(x) goes closer to 4. This is the point 4 here. And similarly, as x comes closer to from the right, f(x) comes closer to 4. This we will write it in just 2 words. These two columns tells us that as x goes closer to 2, from left, f(x) goes closer to 4. Similarly, these two columns tell us that as x comes closer to 2 from the right, f(x) comes closer to 4. Symbolically, we will write it like this: x arrow to negative. As x goes closer to 2 from left, this will be represented by x arrow to negative, apex goes to 4, we write it as apex arrow 4. Similarly, we will write this as x comes closer to from right as x arrow to positive and apex goes to 4. Note that when it is from the left it is to negative, when it is from the right it is to positive, and these things are read as x approach to 2 negative, apex approach to 4, x approach to 2 positive, apex approach to 4. This again we can write it like this: lim x goes to 2 negative, apex equals 4. And this thing we can write as lim x goes to 2 positive, apex equals 4. Where this representation, this and this are the same thing. This means this is read as limit x approach to 2 negative, apex equals 4, and this is read as limit x approach to 2 positive, apex equals 4. This is said to be the left hand limit, and this is limit, and this is said to be the right hand limit, left hand limit of apex at 2 and right hand limit of apex at 2. And if these two are equal, if limit apex approach to 2 negative, apex is same as limit x goes to 2 positive, apex, then we say that the limit is independent of whether we are taking pointers from the left or whether we are taking points from the right, and in that case we say that limit exists, and we write limit x goes to 2, apex equals, here it is 4. So when we say limit at any point, here 2 exists when the left hand limit of apex at that point is same as right hand limit of apex at that point, and the left hand limit of apex at that point is same as whenever x goes to that point from the left, apex comes to some closer to some point, and similarly the right hand limit. Now here we note that, let me go up, here we know that apex was defined as x square minus 4 upon x minus 2, and apex was not defined at x equal to 2, but even then we defined a limit of apex at x equals 2. We also observed that although apex was not defined exactly at a point x equals 2, but it was defined to the left of 2 and to the right of 2 at all the points. In other words, apex was defined in the neighborhood of 2 except at x equals 2. Whenever anything is defined in the neighborhood of a point but not at that point, that there we say it is defined in the deleted neighborhood of 2. So apex here is defined at in the deleted neighborhood of 2. So whenever we look at a limit of any function at any point, that function has to be defined in the deleted neighborhood of that point. So with this, we are now in a position to define limit of a function at any point a. So here is the definition. Let me write definition with this color. Here is the definition. I will write let apex be a function which is defined in the deleted neighborhood. We write NBD of a, any point a, then if limit x approach to a negative f(x), that is the left hand limit, is same as limit x goes to a positive f(x), then we say that and is equal to L, then we say limit of f(x) at a is L, and write limit x goes to a f(x) equals L. Okay, that's it for this video. Thank you for staying with me. In the next video, we'll be discussing what do we mean by saying limit of a function at a point does not exist, and how does the graph of the function look at that point. For more such videos, please subscribe to my channel by hitting the subscribe button and click the bell icon. Thank you once again.